welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course, Statistics 101, Introduction to Statistics. In less than 10 minutes, this video demonstrates how to use frequency distributions. Let's get started. We can use frequency distributions to better understand our data. Perhaps the quickest and most powerful message a frequency distribution communicates about a data set is its shape. Now, to see the shape of a frequency distribution, just imagine there's a line connecting the top of each of the bars in your frequency distribution. So for the frequency distribution that you see there on the screen, its shape would look something like this. This shape is very special because it roughly approximates what's called a normal distribution. Now, we're going to be talking about normal distributions much more in depth later in the course. For right now, all you really need to know is that the normal distribution has a very characteristic bell shape, meaning it looks like the outline of the shadow that a bell would make. The frequencies start low, come to a high point around the center, and then come back down in a symmetrical fashion. Now that word symmetrical means that if you drew a line down the center, each half would look like the mirror image of the other half. When you're judging subjectively whether or not a distribution shape is normal, don't get caught up in little deviations and such details. Just look for the general trend or approximate likeness to the shape. So, for example, what you see there on the left side of your screen is a quote-unquote perfect normal distribution. And if you compare that with what we see with the frequency distribution there on the right, you would say, well, it sort of is, but it sort of isn't. If you get caught up on little details, you might say that it's not. But, for our purposes, you're just going to look for the general trend and approximate likeness. So we would say that yes, this distribution, it would be subjectively judged as approximately normal. Now, frequency distributions sometimes have gaps. And gaps are important to note because they can indicate the presence of more than one population in your data set. Now, the reverse is not necessarily true. A gap often indicates the presence of more than one population, but just because you have more than one population does not mean that you're going to have a gap. It depends on how many classes or categories or bins you use to create your frequency distribution. If you have too few, it can hide the gaps that would indicate the presence of more than one population. Let's look at an example. Here's a frequency distribution for a data set of the weight of U.S. pennies. We've got a sample of pennies here, and we weighed them all. We found that 18 of them are between 2.40 and 2.49 grams. 19 of them are between 2.50 and 2.59 grams, and so on and so forth. So notice there's a gap here where there's no data being reported. Okay, this set of zeros that you see right here is indicating a gap. There's no data in any of these bins. This means we actually have two populations of pennies. Okay, one up top in a lighter weighted region and one down below in a heavier weighted region. Now sometimes gaps exist where very little data is reported for a category. That means you don't necessarily need to look for a 0 to identify a gap. Sometimes it could be, just like a 1 or a 2. It really depends on how many data points you have, how many categories you have, what the frequency counts in those categories are. But generally speaking, you are going to be looking for zeros to indicate your gap. Now, in this example here, you've got two different populations because there was a change made in how the U.S. Mint manufactured pennies. This change occurred, in 1983. So if your penny was manufactured before 1983, then your penny was composed of 95% copper and 5% zinc. But after 1983, pennies began to be made with 2.5% copper and 97.5% zinc. Zinc, being a less dense metal than copper, is much lighter than copper. And so the pennies that we see up top that are weighing less were made after 1983. The pennies down at the bottom of the frequency distribution were then made before 1983. Now, you might be wondering, hey, what's the big deal with 1983? Why the change? Well, quite a bit, as it turns out. 2 years prior, in 1981, there was a coup in the country of Chile. Now, Chile is one of the world's major producers of copper. Well, there was a coup that took place in the country. The military took control, and they didn't take too kindly to the United States because, quite frankly, we had interfered often in their internal affairs. I mean, as a matter of fact, The U.S. government actually sponsored some of what was happening, clandestinely, of course. Thank you, CIA. After the coup, a guy named Pinochet gained power and was basically torturing his own citizens. I mean, there's human rights violations galore. It's an interesting story to look into if you don't know anything about it. But long story short, we had to make some choices when our supply of copper got reduced and pennies did not win. The frequency distributions often allow for in-depth analysis. So let's look at this example here. This frequency distribution is showing the heights of a sample of people at Vassar Road Elementary School. So you've got definitely one population here, and there's another population, down towards the bottom, because you see that gap that we've got there in the middle. See the zeros? Okay, so this is indicating we've got two different populations here. Now, what would actually explain the two populations here? Why would we see two populations here in the frequency distribution? What do you think? I'm going to give you a moment for you to come up and make your response. Okay, if you're having trouble figuring out why we would have two populations here, think about what the data represent. The data represent people at an elementary school. So what people do we have at an elementary school? Well, you've got some people who are really short. Those are the kids. And then you've got other people who are much taller. Those are the adults, the faculty, the staff. So identifying gaps, as well as the shape of your distribution, can actually reveal characteristics of the underlying data. So here we've got a larger population of kids and a smaller population of adults. There's two populations there in your frequency distribution. Now, if you make frequency distributions from the data that we saw earlier for, let's say, the Best Actress and Best Actor Oscar winners, okay, you get what we see here. If you want to see if you can make these on your own, feel free to pause the video and then go into StatCrunch and make these frequency distributions on your own. Okay, the one on the left is for Best Actress, the one on the right is for Best Actor. And with these two distributions side by side, what can you conclude from comparing them? Well, one thing you can do is observe the shape of your distribution. Where is the bulk of the data located in each? So for the Best Actress distribution, the data seem to be centered towards the left. So if we put a bar around the median point of our distribution, we see that, we're kind of centered on the left side of our graph. But for the Best Actor distribution, there on the right, the data seem less shifted and more centered. Now, look at the categories those centers correspond to. It seems that when it comes to movie stars, we like our women a little younger and our men a little older. You can also observe the tails of the distribution. Now, the tails are where we have relatively less data. Notice the age ranges for the tails on the right. It seems we have higher tolerance for older men in movies than we do older women. Now, look at the tails on the left. There's not much of a tail there for the ladies, okay, showing a clear preference for seeing 20-something ladies than 20-something gentlemen. Do you see how observing the shape of the distribution and where the data are amassed within a distribution can reveal information about the underlying data? I mean, these skills are like any other. They get better the more you practice them. So don't get discouraged if you can't see right away everything there is to be seen. Just keep practicing and you can improve. After all, practice makes perfect. And that brings us to the end of this mini lecture. Hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video. Howdy peeps, I'm Professor Curtis of Aspire Mountain Academy, and I hope you enjoyed this free sample mini lecture from my Stat 101 course. This is a course that I've worked really hard to develop. It's taken me a while to get through it, and I hope you enjoyed this free lecture. If you want more like this, then you need to sign up for my Stats 101 course. So go to the link there in the description down below the video. If you like this video, go ahead and give it a like and subscribe to the YouTube channel, and I will see you in the next video.